Okay, good morning, good afternoon, and good evening, everyone. I'm really excited for this talk today. We have an opportunity to talk to one of the maximum experts in the field of weather stations, low-cost weather stations in the world. And today we're here to kind of talk about how it's possible to develop low-cost weather stations and how it's and guide you to developing your own for the weather station challenge that we have in collaboration with the ITU. So I'm really excited for the opportunity to host this talk today. We'll go through a couple of different sections, and you'll have the chance to ask questions throughout. So make sure you get your questions ready and ask them when you have questions. Okay, so without further ado, let's get started. So today we're going to talk about development of low-cost observation networks to support weather and hydrology applications. As usual, we're here thanks to our partners. You can see here are all our tinyML strategic partners. It's quite a few of them, and we'll say a few words about them all at the end. So really excited, and thank you all for supporting the tinyML Foundation and this tinyML challenge. Cool. And then I wanted to tell you all that there is an interesting event happening on September 27th, the tinyML Neuromorphic Engineering Forum, led by Professor Charlotte Frankel. And again, this is going to be on the 27th of September. So if you're interested, make sure to follow this. And then really excited about actually participating and co-chairing the tinyML EMEA Innovation Forum this year. So this is actually our first EMEA forum. Last year it was the first one in general, but it was fully virtual because of the pandemic. This year we're all going to be in Cyprus, and I'm really excited to have the chance to meet some of you at this event. So make sure to book your hotels if you haven't done so yet, because the hotel rates are ending. Our kind of special rates are ending this week, and the prices of the conference ticket are going to go up next week as well. So make sure to register now if you're interested, and see you all there. Okay, and then one more thing about the tinyML Smart Weather Station Challenge. So today we'll have this talk to kind of walk you through what, some of the research around this, and a specific section led by Jenny on how to implement algorithms to actually solve this challenge. But on the 23rd of September, you can join us from 4 to 5:30 CST or 7 to 8:30 AM PT for an open hour, office hour time to ask any questions you might have on what you've been doing, what challenges you've been encountering, and any other things that you might be wondering. So see you all there if you've got questions. And then a couple of notes. If you haven't done so already, make sure to register on the meetup, the tinyML meetup. It's a huge community, about 11,000 members now in 46 groups in 37 countries. So it's huge, and it's growing very fast. So excited to be part of it, and invite you all to take part in this growing community as well. Make sure to also follow us on LinkedIn for updates and news, as well as on YouTube. So subscribe to our channel, because all the talks that you see here on the tinyML channel are actually going to be hosted on the YouTube channel. So make sure to follow so that you can get new updates. Okay, and now I'll introduce you the speakers. Again, I'm really excited to have here with us our two speakers. The first one is Professor Paul Kucera. He's the lead. He leads the International Capacity Development Program at the University Corporation for Atmospheric Research, and he's an expert in weather radar, development of weather observation networks, satellite meteorology, numerical weather prediction, weather modification assessment, and international program development for the modernization of hydrometeorological services. I hope I read that well. And also, he's been recently working on a project to actually modernize and develop low-cost weather stations that can be deployed around the world. And that's the reason for having him here today. He's going to speak to us about the opportunities and challenges of developing a low-cost weather station. So I'm glad to be able to welcome him and hear his point of view. Following Paul, we'll have with us Jenny. Jenny is a senior user success engineer at Impulse, and she will be talking to us about how to develop weather station or algorithms for detecting weather station. Apologies for this. How to develop algorithms for detecting wind and rain, so that you can use that to develop your weather station. And without further ado, Paul, it's your time, and the stage is yours. Take it away.
All right. Yeah. Thank you for that nice introduction, Alessandro. That was very nice. And I really appreciate the opportunity to talk to this forum today about our project. I also have our colleague on here, Martin Stinson, is kind of the co-founder of this project. So today I want to talk about our development of low-cost observation networks to support weather and hydrometeorology, and actually we're also working on air quality applications now, and I'll briefly talk about that in this presentation today. But yeah, so this kind of overview of our experience going through this process to kind of expand those networks around the world. So just as a kind of introduction, it's about 8 years ago we started this project, and the project's called 3D printed automatic weather stations. It was launched to support disaster risk reduction programs. So a lot of the areas around the world, especially in the least developed countries, there's very few, if any, weather observations in these areas, and these are critical for observing or detecting high impact weather events such as floods, droughts, and other events like that. And so, but weather stations in general are very expensive and hard to maintain. So this idea is that, can we build something that is low cost but sustainable, and that we can expand that network to provide those observations to detect these high impact weather events, and so that we can, so our partners can then use that information for applications such as early warning, forecasting, water resource management, things like this. So it's really focused on is reaching out and providing additional information for those most vulnerable communities. So that's the kind of the sum of our project. We've been going, like I said, for 8 years. We've done a lot of development since our initial deployment, a lot of improvements in terms of reducing the power consumption and making these even more sustainable for the different regions. So why 3D printers? 3D printers have become a really inexpensive technology. So you can get those anywhere around the world. The 3D printers that we use are just kind of the middle of the road quality. And they cost on the order of about $2,000 each. So not overly expensive. And then they can be used to print, many weather stations. And these stations, the whole cost of a station, including the printing, the sensors, the solar panels and batteries, it's on the order of $300 to $500, and that range kind of depends on what kind of communication and solar solutions are available in the countries we work with. We integrate into our system low-cost, reliable microsensors, and the whole idea is to build capacity in country so that they can be fabricated, assembled, and deployed locally, instead of having to have weather stations shipped from a different vendor and installed and try to maintain. They're built in country and build that capacity. And the whole idea is, think of it as kind of like print and replace components when they fail, or animals get in and maybe damage a sensor, or they vandalism, whatever. You have the capability of replacing your components or your whole station by having this technology built locally. And this kind of enables our partners to have ownership in the whole framework, so they can build it and then also maintain it. So for me, when I make something myself, then I know how it works, and it's a lot easier to maintain than try to understand how to maintain something that you didn't build yourself. So all these are kind of a reasoning to move forward with this project. And here's an example of our station on the right. This is a station located in Uganda for a study we did around Lake Victoria. So here's just kind of a summary of the different sensors, components of our weather station. So we started off using a Raspberry Pi single board computer as our main framework for data acquisition, processing, and communications. We're moving away from that because of the high power consumption and the need to have these stations placed in remote areas with no commercial power. So we're moving to micrologger, data loggers like Arduinos that have a much lower power consumption. And then we build everything, the housings of the sensors themselves. So we have an anemometer to measure wind speed, a wind vane to measure wind direction. We measure light, so visible and infrared light to help with agriculture applications. We have what's called a tipping bucket rain gauge to measure the rainfall rate and rainfall accumulation at the site. And then on the left, picture on the left is a radiation shield. And inside that radiation shield, we measure temperature, atmospheric pressure, and the relative humidity at the site. And then for power and communications, we include a solar panel and battery backup for these remote regions. And with the new micro loggers now, these panels are much smaller than the one shown here, which is to support the Raspberry Pi in the past. And so we have a variety of ways to connect the systems to the network. So you can send them up through direct connection, wireless, cell modems. We have a satellite communication solution, though we've never had to use it since it's somewhat expensive, and then lower networks. So there's a variety of ways to get the data in near real time back to a database that can be used for decision making in a variety of applications. So in terms of configuration, as I mentioned, these are the parameters that we measure. We provide real-time data access to either a remote or local data archive. We typically set our stations to record every 1 minute. However, depending on your application, it could be the time frame between measurements could be longer, say 10, 15 minutes, or even an hour. It's all configurable in the Python code that we provide with the systems. And then I mentioned the wireless communication. So I'll show a map a little bit later, but we've deployed these stations all over the world. Here's just examples, some of our setups from Barbados, Uganda, Vienna, Austria, and also in Kenya. Just wanted to highlight part of our deployments and our projects that we've been working on. There's a lot of interest not only for weather information, but also other parameters to help with monitoring of, say, air quality. So we have a small project to kind of add or provide a module onto our 3D pause weather station, and that's air quality. So we've been developing sensors to integrate into 3D pause that would measure particulate matter, so looking at dust, surface ozone, VOCs, NOx, SOx, methane, carbon dioxide. We've also been testing lightning detection sensor to provide information in areas where, in these remote areas where you don't have access to, say, satellite or weather radar to determine where there's severe convective weather. And then this lightning detection can then help determine where you might have severe weather without access to remote sensing. So yeah, lots of applications in this framework, from air quality monitoring for health, and like I mentioned, local severe weather detection. We've also been working on soil sensing. This has been a strong interest from partners around the world to really understand what's the soil conditions for, especially for agriculture applications, but also for areas where it's prone to floods and flash floods. So if the ground is saturated, you'd see that you would have the impact of additional rainfall would cause floods much quicker than, say, the soil was not saturated yet. So we're working on low-cost sensors for soil sensing. And then something that we've developed recently and are now deploying is using an ultrasonic sensor to measure the depth or the height of various parameters. So we've developed a stream gauge, so measure water level in a stream or a canal, either for monitoring for when you might have flood conditions or water resource management in a canal. Storm surge monitoring, we're working with the National Hurricane Center here in the United States to provide a low-cost storm surge sensor so that they can be deployed in vulnerable areas where tropical storms, cyclones, hurricanes can cause damage, to provide some early warning information, but also provide input for their storm surge modeling to provide that early warning. And then snow depth monitoring, we've also been working a variety of groups to, again, focus on water resource management. So using the same sensor to measure snow depth for that water resource management. So here's just an example of our some of our deployments. The left image and the middle image is our various deployments of our stream gauge sensor, and then on the right is a deployment of our snow depth sensor in California. So again, used for flood monitoring, early warning, water resource management. All can utilize these low-cost measurements that really help improve those decision-making activities for those different applications. Here's another deployment. This is in the United States. We've deployed a system for tidal monitoring. So looking at a tidal gauge against the same principle, same sensor, now different application. Looking at tides, and also we've added wind speed and wind direction to look at how the winds might impact the diurnal tides in this region. And you can see on the snapshot here of the time series on the bottom, just showing that nice diurnal cycle of both wind and stage height, or the tidal height from the daily diurnal cycle of the tide. So again, low-cost measurements provide really great information on these kind of parameters. As I mentioned, we're working with the National Hurricane Center. We deployed several of these sensors for storm surge monitoring. Here's an example. This information is critical for looking at the storm surge from landfalling tropical storms. And then this information that can be used for early warning, also post monitoring of how high the storm surge was to help, again, improve upon the forecasting of the future. Here I wanted to show you, this is just if you haven't seen 3D printing before, this is just a nice video of showing some of printing of our 3D printed weather station. This is a leaf of our radiation shield being printed here. We wish we could print that fast. It's a much slower process, of course. But just going to show you how the housing of the sensors are built layer by layer through 3D printing process. And here's a printing of some of our connectors in this case. Right. So in terms of the materials that we use, we started off using ABS for our design. ABS is shown here. The picture on the bottom left with the sensors that are in yellow. This was one of our, if not our original station, printed with ABS, and you can see that ABS in the sun and the elements becomes very brittle and can crack easily. So we moved to through kind of our research to a plastic called ASA, which is very UV resistant and holds up quite well. The radiation shield on the left of that picture on the bottom there shows how the radiation shield looks in great shape even after several years of being out in the field. You do have to kind of worry about the opacity of the plastic to make sure that you don't get too much sunlight onto your sensors. But overall, this ASA plastic has been a great solution for deploying the stations in the field. We have some of our original stations with ASA have been out in the field now for 6 or 7 years. I think, yeah, at least 6 years, if not 7. And they're holding up great to the elements. And so that's been a great success. Our original idea is that we would have to replace sensors at like every 2 to 3 years. That was kind of our original design, but we're seeing that, especially in areas where it's not like in a marine environment, they last much longer than we expected. So a great result from our initial testing and development. So some of the pros of using 3D printing for developing your stations. So it's really inexpensive technology. You can create complex components. It's great for changing. It's flexible. You can change your designs on the fly. Great for prototyping, seeing how different designs work, making new designs. Probably the biggest limitation of using 3D printing is really slow to fabricate. Depending on how you set up your printing, it takes on the order of 1 to 2 weeks to create a full weather station. And as I mentioned in the previous slide, that there is kind of limited range of materials that seem to work well in the elements outside in the environment. So, everything that we've been working on is open source technology. We really want people to take advantage of what we've developed and use it for their own systems and their own projects. So Martin, who's on the call here, has developed all the designs using open SCAD, and here's just examples, some of the snapshot of the code for the cup for the anemometer. And so these are all created into STL files, which again we make available, so you can actually create your own station. Going to our project website, which I'll show here toward the end of my presentation, and then use that to make your own station. So just to kind of go through some of the sensors I mentioned earlier, here's the design for our 3-cup anemometer. We did our initial testing in a wind tunnel that NOAA here in the US has for instrument testing. We tested the system up to Cat 5 hurricane speeds, which is about 70 meters per second. It held well for 10-15 minutes, which is great. But we also use that information to improve upon our design so the system can even last longer now that we've done these improvements in these tests. So we're quite happy with our design of our system. Here's the different components, just kind of broken out. The 3D printed components, the electronic components, the wiring, everything else. You see that there's quite a few different components that are printed and then assembled together for the anemometer. Here's just kind of go through. Here's the wind vane, again showing the different components. I try to remember, and Martin may be able to correct me if he wants, but I think there's on the order of 100 to 120 different components that are printed for the station. Here's an example of our tipping bucket rain gauge. So the tipping bucket, so it's been calibrated. Each station's been calibrated to measure each time the bucket tips. It's equivalent of 0.2 millimeters of rainfall that has fallen at the site. And so each time it tips, it sends a signal back to the data logger and records the time of tip. And you know that each tip is 0.2 millimeters of rainfall, so you can then start accumulating the amount of rainfall for any rainfall event. You can also use it for rainfall rates. So, more tips in a short period of time is a higher rainfall rate, and so on. So it's it's kind of a universal design. We followed other designs that are out in the industry in terms of developing our system. And here's again just the different components that go into the weather station itself. This is the rain gauge itself. This is the instrument that takes the longest to print. As you can see, the funnel itself, there's a lot of plastic involved, so it does take a considerable amount of time to print this component. And then here's just the radiation shield. Again, we print the leaves of the radiation shield, and then we integrate the temperature, pressure, and humidity sensors inside of this. And then there's just natural ventilation that flows through it to keep it from overheating. We have the mesh grid, so that keeps at least the biggest bugs out and other critters that like to get into this sensor itself. So seems to work pretty well. We haven't really had any bug issues. Occasionally a frog or two like to live underneath the leaves, but nothing that really impacts the measurements themselves. And again, here's all the different components of the radiation shield shown here. All right, so one of many questions that we get is how well do these systems measure the actual conditions in the atmosphere, in the environment? So early on, we did a lot of testing of our initial systems here in Colorado, and just south of Boulder, Colorado, where we're located. We have a field test site called the Marshall Research Facility. It has in the order of about 50 different stations from different vendors from all over the world that have been calibrated and referenced. And so we could use those data to compare to our low-cost measurements. Also, NOAA out by Washington, D.C. has also a testbed center, a similar configuration of sensors, and we were able to use those reference measurements for intercomparisons. So I just want to show, just kind of like highlight a couple things. Here's just one test comparing the pressure. So on the y-axis is the measurements from the 3D pause station. On the x-axis is the commercial reference sensor. This is just raw values, no quality control, showing comparisons for a little less than a year. And you can see that looking along the one-to-one line, surface pressure matches up quite well with uncertainty in the field of about 0.5 hectopascals. Which is really good for in this intercomparison measurements themselves. Our wind vanes seems to match up quite well. Here's an example of our Windmay vane measurements matched with a wind vane at the NOAA Testbed Center. And again, showing that in this case, the wind rose, the predominant wind in the Washington, D.C. areas from the west-northwest, and both our measurements on the left, the 3D pause, and on the right, the NOAA Testbed Center wind vane, show that we match up quite well with these measurements. So errors of less than 5 degrees in terms of the direction of the wind in these comparisons. We've also been doing a lot of internal testing to look at the response of the anemometers. So we've also taken our a whole set of our anemometers that we've printed, assembled, and compared them to wind tunnel measurements here. This is an example of measurements at the University of Iowa. We've also looked at some of the measurements in the NCAR wind tunnel. And what we found is that the 3-cup anemometer is really durable for high wind speeds. The calibration is very consistent for low and high wind speeds. Wind vane, as I mentioned previously, also seems to work well. So we're quite happy for a sensor that costs on the order of $10 to $15 US can perform quite well compared to these very high-end, high-quality reference sensors that we've been comparing them to. Here's just again a picture of the wind tunnel at NOAA, doing our testing in the wind tunnel, looking for both calibration and failure conditions. So here's a summary of our measurements of our internal measurements comparing in the field. Again, our measurements, we're very happy with how they compare with both the resolution and the uncertainties of the different measurements from temperature to rainfall. But what we're doing now, and we've just started actually a couple weeks ago, is we've been working with the World Meteorological Organization, and then working with the Turkish State Meteorological Service at their regional instrumentation center to do a complete independent evaluation and calibration of our systems, and get that independent evaluation to have that report to show what is the quality of our data going forward that can be used as part of the deployment process, and to see if it meets the uncertainty, meets the needs of the application, for example. We've done comparisons in the field. We've deployed sensors at schools around Kenya, and then have the students take manual measurements, say rainfall, along with our automatic measurements of 3D pause. Again, the comparisons show really good results of these intercomparisons of the manual, the verification data, along with our system itself. So. Yeah, and here's again just to highlight, we are working on this intercomparison study with the Turkish State Meteorological Service. This is a 2-year test that will be ongoing. We'll be doing laboratory calibrations and then field testing. Here's an example of the 2 of the sites we deployed about two weeks ago in Turkey, and each site has 3 stations. To look at the intercomparisons of each station along with the reference sensors. And in this test, our group built 2 of them, and then the Turkish Met Service built the 3rd one. So we're looking at how they compare and how different groups fabricated the sensors themselves. Just another, some more examples of our stream gauging. Here's a comparison of the stream gauge, looking at water level in this river in the state of North Carolina, comparing it with the U.S. Geological Survey stream gauge. And again, our measurements are in gray. And again, this is raw data compared to average data from the USGS gauge. And you can see that we're capturing the variability of the water levels in the river as shown here. Here's going back to that tidal gauge, looking at again the diurnal cycle of the tides. And you can see here there is a little more variability. We're capturing the peaks and troughs of the tide each day, but there is some variations on the low tide and high tide compared to the USGS gauge, which is co-located on that pier shown in the image on the left. So again, there's always room for improvement, and we've been working on improving on our designs. All right, just to kind of get to the end of the talk here, kind of like where have we been? So we've deployed stations in 12 different countries. A lot of our initial efforts been in Africa, some of the least developed data sparse regions, Kenya, Uganda, Zambia. We have a few stations in the United States, but most of it is with our partners, say in Barbados, Curacao, Trinidad in the Caribbean, El Salvador in Central America, and then as I mentioned, we have some stations in Austria, and we have Germany, France, and in Turkey, kind of our test bed there. So part of our project, we work. Our whole goal is to train people to make their own stations. So we offer workshops that last anywhere from 7 to 10 days. And then we often, part of the project is we provide all the materials to get an initial weather station network started. So on the order of 20 stations can be built with the initial training that goes along with it. So here's I want to kind of highlight one of our most successful partnerships is with the Barbados Met Service. So the Barbados Met Service, really a tiny island in the eastern part of the Caribbean. Working with their Met Service, they have a goal of deploying 100 of our 3D PAWS designs, and they're making them all the station themselves, deploying them around the island to get a complete coverage of that small scale rainfall, temperature, wind variability, to provide that early warning to the public on this island. And they've been extremely successful. So they're already up to, I think now it's, as of today, it's like 65 stations out of their 100. So they're systematically going through and building out this network, which is a great success story. Of we taught them how to do it, and they've just taken off and doing everything independently themselves. Part of our project, everything is open source. Data can be accessed through our data web portal, which is called CORDS. Data can be stored locally on the data logger itself, especially with the Raspberry Pi. You could store, 2+ years, I think even more than that. And then we've also built links into our code so that you can also send data to other data portals as needed to access your own data. So here's the website for our project. So in this on this website, basically all the details on how you would go through and make a 3D PAWS station. So there's details on the system costs, how we're doing the calibrations, the designs of the instruments, the wiring, how you build the frame and assemble it, the different software, and then the downloads of all the code and designs of the station itself. So this is a great resource. This has been supported by the USAID program here in the US to help build out this capacity and help with this disaster risk reduction, which I mentioned at the early part of my talk. As I mentioned, we do hands-on training for the process of the 3D printing, the assembly, fabrication assembly shown here, and then deployment and maintenance of the systems. So the training provides kind of end-to-end on how you would establish your own weather station network. So just to summarize, kind of what I talked about today is this low-cost observation network. It's to provide this innovative solutions. to really increase environmental monitoring capabilities. The existing 3D POS capabilities include temperature, pressure, relative humidity, winds, rain, solar monitoring. We have that water level system now. We're working on air quality, for example. And some of the applications that we're hoping to work on or are working on, looking at early warning, flash flooding, storm surge inundation, different decision support for water resource management, agriculture, port operations, things like that. So I think with this project that the tinyML, this could be a great opportunity to take all these data and use it to really kind of help solve some of these applications moving forward. So that would be a great partnership in applications. So with that, I'll stop here, and I appreciate the time to talk to you guys today about our 3D POS project. So yeah, thank you.
Paul, thank you so much for that overview, and really great to see that you guys have done quite a bit of progress in the last few years. As you know, we've asked our participants here to solve the challenge of developing a low-cost weather station. We've actually asked them to also, just to complicate things, to do it without moving parts, right? So the question really is, can you develop a sensor that doesn't have moving parts? Because we know that requires obviously an upkeep, and one of the challenges that we saw with weather stations in remote countries is remote parts of the world is actually the challenge with effectively going to fix them when they break, or changing parts, or even just figuring out whether they're broken or not, right? So for that, we've kind of challenged our community with this additional requirement. But yeah, so exciting to know that there's been a lot of success from your side and from the teams on developing things that actually work and are low cost and can scale to multiple weather stations.
Yeah, that's great to kind of develop a non-moving part weather station. It would be a good win, because that is kind of limitation. Say at the anemometer, if you're in a cold weather environment, if it's snowing or freezing rain or something, the anemometer tends to lock up, right? So you won't get the measurements then. So having, say, an anemometer that is sonic or some other method without moving parts would really help with that particular problem, for example.
Yeah, exactly. And also it's for the water, right? The bucket that also has moving parts. So what we've asked our community is, can you develop a sensor that doesn't require effectively moving parts, and therefore needs some sort of like processing on the device itself? And to that, obviously, tinyML is a solution. So can you do things like wind monitoring or rain monitoring through the sound, for example, right, of rain or wind, using just a microphone, or other similar things. And we've had a lot of creative ideas, and I'm excited to see more of what's to come. So just a couple of quick questions. So you mentioned that you've got a pretty big test facility. I would love to kind of ask you on behalf of all participants, would there be chances perhaps to have the winners maybe test the solution within your testing facility? Is that something that you open up for public use, or?
Yeah, definitely. Yeah, exactly. Yeah, that'd be great. Part of that test bed is to test new sensors, so we could add it to our test bed of 3D POS, and then it'd have access to the reference sensors that are on the facilities themselves. So yeah, that would be a great partnership. I'd be happy to help facilitate that. Awesome.
I'll ask you another question. Do you think eventually in the future it will be possible to share the data, or to send the data to WMO and actually make these weather stations, kind of full-fledged weather stations that are part of the bigger network?
Yeah, that's our goal, is to get acceptance from WMO so that it can be part of the I'm forgetting the name the net. WIGOS, I think maybe is the name of the network, but yes, to provide not only I call the climate reference stations, but also these low cost stations to really build out that network. So yeah, we're working with WMO on that whole idea of being able to supplement, I guess, with these additional measurements. So we're hopeful that in the future, all these data will be accessible through the WMO data portals.
Awesome. And then one last question from the audience. What's the order of magnitude of volume of data generated locally, processed, and communicated to the network? Any insights on like the amount of data that you're generating locally?
That's a great question. We could. I mean, the data volume itself is small, but the number of records is large. It's on the orders of millions of observations. So each parameter every minute. So we measure eight parameters. So you can kind of think of how quickly we have all this 1 minute data that's available. But in terms of the size of itself, it's still really small because it's just these point measurements. So.
Awesome. Okay, that sounds good. Cool. Okay, so moving on. By the way, if you've got more questions for Paul, feel free to ask them in the Q&A box. We'll take them at the end of this next section. In the meantime, I just wanted to remind everyone, if you haven't done so already, you can register to our challenge, where you'll have a chance to win a lot of interesting prizes or a lot of great prizes, and have a chance to actually contribute to this wider problem of collecting data, weather data around the world. So if Olga, if you can please post the link to the challenge, that would be awesome. So for people to register if they haven't done already. Just moving on, I'll introduce the next section. So we'll have now Jenny talk about how to develop effectively a tinyML model using Edge Impulse for solving effectively what we just discussed. So how to detect wind and rain and other parameters without using moving parts, right? So with using just standard sensors. So Jenny, take it away.
Hi, everybody. Thank you, Paul, for the interesting talk. Weather sensing is really cool. I actually just recently did a weather project with weights and biases for detecting weather from images. So there's lots of different ways you can detect and track certain weather patterns. And what I'm just going to be showing you today is how you can use Edge Impulse to develop and deploy tiny machine learning models for these types of devices, like the ones that were just described. So this is our website. Edge Impulse is completely free to use, so feel free to sign up today by just clicking on Get Started on the homepage on edgeimpulse.com. Just going through the studio of Edge Impulse, this is what it looks like when you've logged in and you've created a project. I'm just going to be going over a use case where I am determining what type of bird call is being heard by my device's microphone. But you can extrapolate everything that I'm describing here today to another type of use case, like using a microphone data on your device to determine if it's raining or if it's windy outside, for example. You can also use this same workflow for any other type of sensor data that you desire as well, including things like temperature, humidity data, pressure data, even all of those things combined. So there's a lot of things that you can do in Edge Impulse, and it's pretty limitless here. But today, I'm going to be describing bird sound classification using Edge Impulse. So this is the project dashboard. Every dashboard is equivalent to one machine learning use case, the one I just described. You can collaborate on your project with up to 4 other people on a free version and up to unlimited collaborators for enterprise versions as well. We have many, many different ways that you can connect your devices to your project. And this is a really great way. If you already have data, you can just upload it via a CSV file or any other type of file on your computer. You can also connect any fully supported development board, like a microcontroller. You can use your mobile phone to collect audio, use your computer. You can also upload data from any device, or if you have data in a cloud bucket, like Amazon Web Services or Google Cloud, you can also connect your bucket directly to your Edge Impulse project and start developing your machine learning models. And all of this information about how you can upload data and label your data into your EdgeImpulse project is available in our documentation at docs.edgeimpulse.com. Need to move Zoom out of the way. Moving on to data sources, don't want to go into too much of this today, but data sources is also available in our documentation. Just click on docs and you can read more about what this feature does because we don't have much time left. Data acquisition, you can see all of your data that's been uploaded into your EdgeImpulse project. You can also label it here and you can preview what the sample looks like. So again, this will change depending on the type of sensor data that you've uploaded. Because it's audio, obviously you can click play and listen to the audio data. If you had accelerometer data, you'd see the XYZ axes here. If you had temperature or humidity or pressure data, you'd also see that data here. So you upload all of your data for your training data set, your testing data set, and then you can also have access to a data explorer as well. So say I want to only upload 10 to 20 minutes of weather data for my specific sensor, but I also have another 60 minutes of data that's been left unlabeled. I can do that. I can automatically label all of my 60 other minutes of data by using the data explorer. It will train a model and it will sort of predict exactly what these other pieces of data are supposed to be labeled even before you've deployed a model to the edge. And again, more documentation about this is available in our documentation site. So for this project, I have 3 different machine learning classes: noise, rose-ring parakeet, and house sparrow. And again, this is just a classical audio classification project. It's not keyword spotting because we're not doing human audio in this case. We're just doing non-human nature sounds. So we have a noise class for all of our backgrounds. We have individual samples for the sound of a house sparrow and a rose-ring parakeet. Say I have a very, very, very long sample that's, a minute to however long you want, and you only have one sample and you just uploaded it. You could then crop the sample directly in the EdgeImpulse tool to any size that you see fit. And then it can also automatically split your sample up into smaller lengths, and it will automatically detect where it thinks is the best area to split the sample based on a DSP algorithm that we have integrated into the EdgeImpulse tool. You can also upload your data through many different types of formats. We also have the EdgeImpulse is also fully driven by APIs, which you can read about in our reference documentation. We have ingestion APIs, we have APIs for adding data, for starting jobs, for everything that you could desire. And if there's something that you're missing or there's something that you can't find, please reach out and ask us about it on the forum at forum.edgeimpulse.com. Moving on, Impulse Design, this is the complete end-to-end graphical representation of designing and training a machine learning model. So on the left, we have our raw data, and our raw data gets passed into our white DSP block where we're extracting the most important features. And then in this blue section here and the neural network, that's where we're going to be training our machine learning model based on the extracted features that we had from our audio digital signal processing block. And this is important because we need to only get the most important features after digital signal processing in order to make sure that our neural network is small and efficient enough to run on our edge device. And again, these are just a web GUI wrapping over pre-written Python snippets for you. And nothing in EdgeImpulse is a black box. You have access to all of the source code from start to finish, and you can see exactly the code that was used in order to create these processing blocks in the EdgeImpulse GitHub. You can also select from a bunch of different types of learning blocks as well. You can also make custom DSP blocks and custom learning blocks. Say you're a machine learning engineer or you're a DSP engineer. You can write your own code and integrate that code directly into the EdgeImpulse platform as well to make designing and training your own machine learning application super, super simple and efficient. So I save my impulse and I move on to extracting my features. Again, this is just a GUI wrapping over Python parameters. So these are just inputs into a Python function. I can change anything here that I want or as I see fit, but I'm just going to keep it the way it is today and click Save Parameters. I can also see throughout the entire process how my model and my DSP and neural network will perform on the device that I've chosen to calculate latency for. So I've generated features. and I can see exactly what my data will look like after the most important features have been extracted. In this case, it looks like a big blob of ball, like a blob, which doesn't really make a lot of a sense in this step, but that's okay. Our machine learning network is just going to have to figure out a little bit harder when we train it in the next tab. So this is, again, if you're a machine learning engineer, you can switch into expert mode, and this is just a GUI wrapping over TensorFlow and Keras code, which again, you can type in your own expert mode code here and just click start training. I'm not a machine learning engineer, so I'm just going to switch into simple mode and use the drag and drop functionality that we have here for designing your neural network architecture. And this neural network architecture will also be automatically generated for you based off of the sensor data that you've uploaded. So today, because I've chosen an MSCC block and audio data as my training data, I've been given this default 1D convolutional neural network architecture. You can also add any layers that you'd like, and we have a bunch of things in here available for you to use for free. So I like the way my architecture is going, and all I did is I click start training, and I get this output here that shows my accuracy and confusion matrix based off of the validation set that was taken out of the training set for use for my model. And there's a bunch of other features in here. I can also see the on-device performance based on the device that I've chosen. In this case, it's estimating for a MacBook Pro. So this model will take 1 millisecond of inferencing time on a MacBook Pro, 6.5K of RAM, and 36K of flash. You can change those latency estimates by going back to the dashboard and selecting the latency calculations. So I can also estimate for a Silicon Labs Thunderboard or a Raspberry Pi 4. Or an ST IoT Discovery Kit, for example. Just choose a device that is most similar to the device that you'll be deploying your model to. Moving on, because we're running out of time, live classification and model testing are very similar. You can directly test that your model will perform as you think it should in the field by clicking classify all. And this passes all of your training data into your trained model and spits out a accuracy matrix of every testing data sample that was accurately or mispredicted to be what its label should be based off of the trained model. A new feature that is coming out specifically for audio data, this feature is coming out on Friday, is called performance calibration, and you'll be able to do even more configuration for your model, specifically in this case for audio use cases, but there's a bunch of other tools that we're developing for other types of sensor data as well. So stay tuned for that and be looking out on our blog for performance calibration release on Friday. You can also version your project. So say that you like your project and it's running well for the use case that your device is in. But I want to adapt my project for a new bird call, for example. I can store my project at this exact point in time with all the intermediate data, all the intermediate model information, and it's basically like a zip file. I can store it up and save it in my project, and I can go back to that version at any point in time in the future. So it makes iterating and developing your models over time super, super simple. Finally, deployment. We have a bunch of different deployment options available for you. The majority of the time, if you do not have a quote unquote officially supported microcontroller with Edge Impulse, you can deploy a C++ library. And this C++ library contains all the digital signal processing code, all the neural network code, everything that you need in order to get started doing your typical model development integration, just as you would with any other C++ library. It can be compiled with any modern C++ compiler, and there's no third-party or external dependencies. And we have a bunch of other libraries here available for you to deploy to as well. WebAssembly is great for doing browser, edge sensor classification directly within the browser. We also have a bunch of pre-built firmware, so you can directly drag and drop a ready-to-go binary with a reference application onto one of our officially supported microcontrollers. Again, this page will change depending on the sensor data that you've uploaded to your training data set. But if you're doing things with like audio or temperature and humidity, we have a lot of boards that have those types of sensors already available that you can directly drag and drop and iteratively develop and debug your model over time. And all of these firmware applications and reference designs are available for free and open source within our GitHub repo as well, github.com/edgeimpulse. And then you just click build, and you can also see the optimizations and quantization options here. And you can deploy as you would any other machine learning project or embedded application project. And that's Edge Impulse.
Jenny, that's awesome. Thank you for the walkthrough. Thank you for the really quick walkthrough, but very, very detailed walkthrough. And there was something you wanted to also share or announce, actually, because we haven't announced it yet. So I'll let you mention that.
Well, it's not out yet, but it's coming soon. So I think Davis actually already asked a question about it in the Q&A. This is a feature that we already have documentation for in the Edge Impulse docs, but it's basically a performance calibration will allow us to test our model on real world or simulated audio streams very quickly and very simply directly within the Edge Impulse Studio. So take a read through on the documentation, and there'll be a more in-depth overview of what this feature does and the value that it provides to you in your audio projects, available on Friday.
Awesome. And there was something about an extra price as well.
Oh, yes. And we also have Edge Impulse is also providing a prize for this contest. In addition to the other prizes, the project that utilizes Edge Impulse the best will win $3,000.
Awesome. So yeah, that's an announcement because we didn't share with the audience yet. So check that out, and good luck with your challenge. And it was around the printed weather station. How often do they fail or lock up due to extreme heat or cold?
Yeah, that's a great question. In terms of the heat, we've deployed them in some very warm environments, and we've not had really any issues with the station performing in high temperatures. The cold, when it also works well. We've here in Colorado, temperatures get down to about -25°C in the wintertime, and there hasn't been any problems, except when we have frozen precipitation like snow, freezing rain, things like that. The tipping bucket will not work for snow, and also the anemometer and wind vane tend to eventually freeze up if there's heavy snow. But in terms of the temperature, pressure, humidity sensors, they seem to work fine even when it's snowing. But yeah, cold and warm doesn't really have a huge impact, like I said, unless it's frozen precipitation.
Awesome. Thank you for that. I wanted to thank the speakers, so Paul and Jenny, for an awesome presentation. And it's good to know that what we've kind of challenged our participants with is not completely absurd. And Paul, it seems like it's not, because you've been developing something similar in the last few years and with good successes. So I'm really looking forward to the solutions that are going to be presented by our participants. And yeah, obviously, you and Martin will also be part of the judging panel, and will be sharing your insights with our participants as well, given your experience. So I'm really excited for that opportunity as well. So thank you again, all our tinyML strategic partners. Analog Devices, Aeon Devices, ARM, DeepLight, Edge Impulse, EMSA, PhotoHub, Greenwaves, GroupD Inc., IBM, Imagimob, iTernis, Clickattack, Microsoft, Not.ai, NXP, OctaML, Prophecy, Hixo, Qualcomm, Reality AI, Wixin, Renesas, SAP, Seed, SensiML, Silicon Labs, Sony, SD, StreamAnalyze, Synaptics, SynSense, and Sentient, and TDK. As usual, this couldn't be possible without all the partners and sponsors. So thank you again. And here is a list of our strategic partners: ARM, Edge Impulse, Qualcomm, Sentient, and the Platinum strategic partners: DeepLight, Clickattack, Reality AI, Renesas, Sony. And here are the gold sponsors. So Analog Devices, PhotoHub, Microsoft, NXP, Seed Studio, SensiML, ST, Synaptics, SynSense, and the list of silver strategic partners. And on the tinyML Foundation page, you can find more details on all of our partners. So feel free to check them out. And with that, again, a big thank you for Jenny and Paul to be here with us today and presenting their view of how this challenge could be solved. And thank you again for all the sponsors and all the participants and the listeners. For all participants, feel free to join us next week, actually 2 weeks from now at the office hours. We'll be answering any questions you might have there live. Also, feel free to ask any question you might have on the forum or email us directly with your questions. Thank you all again for joining.